series, Random Elements. And what I'm going to do is pick an element at random, and we're going to look at what it does, what we can talk about it, some of the practical uses, ways to identify it, and anything else that we can find that's a little bit interesting. Now, firstly, I will close my eyes and pretend I'm not looking at one specific element, and I'm going to go back and forth here to try and pick something. What's this? Interesting. Okay, I don't know how much we're going to get out of this one, but here we have Einsteinium. Guess who it's named after? Let's see, Einsteinium. Again, this is a synthetic element. Elements in this part of the table you can't find, mainly because their nucleus is very unstable. The protons and the neutrons are held together by the nuclear force, which doesn't work when you begin adding more and more protons. It begins to get very weak. And I explain this all in my article on my website, which I will now show. But the general idea is that protons and neutrons attract each other based on their quarks. And the quarks have a nuclear force, which is attractive to each other. But it's actually a residual force. The main force comes in the, the interactions between the quarks, which then build up to interactions between different protons and neutrons. However, in the case of the larger elements, it takes more and more protons and neutrons to do this. Because what tends to happen is that this force is only so strong, and adding more protons puts more pressure from electromagnetism, which makes it very unstable to have them all next to each other. So you have to put more neutrons in, and more neutrons in. And it begins to get a little bit tricky. But this is the general idea for how they're sticking together as quarks. And you can read this article on my website right here. See? Protons don't like extra positivity. No thank you. And the strong force keeps protons and neutrons together. See how happy they are? This explains how it works. But let's look at Einsteinium here. It's in the actinide series, the seventh, transuranic element. Okay, obviously it was named to honor Albert Einstein. They found it in the debris of a hydrogen bomb. Can you imagine cleaning up after a hydrogen bomb? It is the most common isotope. Oh, 253 is the most common isotope. You can produce it from californium decaying in high-power nuclear reactors. Okay, you're not going to find this. It's very, very difficult. It's soft, silvery, and paramagnetic. And of course, very radioactive. Since the nucleus is so unstable, what is happening is it's going to split. But when you split a nucleus, you create radiation. You can also create large amounts of energy, which is, ironically, how you get a nuclear bomb. Because it's so unstable, they split. And you do this billions, trillions, I don't know how many times. With all the different uranium nuclei, they will unleash all that energy that you can see. It is highly dangerous to health in... Okay, do not ingest Einsteinium. This was found in 1952. They figured it out. This is a lot of physics that I cannot do, and I will not attempt to do. Let's see. Oh, wow, they actually have it in a vial. That's amazing. Okay, so you can hold it, unlike other ones. This is a very soft metal. What else can we find about this? It is volatile. There is self-damage because it is so strong, it will destroy the crystal lattice and radiate massive amounts of energy. Is there anything you can do with this? It's very good for nuclear fission, of course. It breaks itself apart. quite certain what you would do with this, though. You can synthesize this. Let's see. They produced an isotope by radiating californium with deuterium. And what did they make this? So they shot a proton with an extra neutron from a hydrogen at californium, and it made this. And then it didn't make this. Okay, so this is just explaining you can make it. You can make a metal from oxides, halides. Okay. I'm glad there is an application part. Yeah, basically, you can't even use it outside of any scientific research. Oh, here we go. They like to use this isotope, 254, to produce ultra-heavy elements because it has a large mass and a long half-life. There you go, 270 days. 270 days until radiation. And you can get significant amounts in micrograms. And they used it to make, what is this? Ununenium. I don't know how they make these names, but this is ridiculous. Ah, here we go. This is interesting. They tried to bombard it with calcium at the Superhelix Linear Accelerator in Berkeley, California, and it didn't work. Not effective. Most of the applications or the reasons you're making these are very straightforward. You're just seeing if you can make larger elements to see what they might do or what you could do with them. But with most of these larger ones, you're just doing this to do it. You're not going to get anything out of it. They don't exist long enough. They break apart. You can't bring them together into a significant amount. It's very unrealistic. But this is what they were trying to create. It's either ununenium or ununenium. Yeah, I'm comfortable with that. Otherwise known as ecafrancium. Ooh, ecafrancium. Francium is one of the what was it? This is the alkali. Yeah, the alkali metals, and they do not like water. When you expose them to water, they violently explode. Okay, they're trying to pick a name, but it doesn't exist. It's hypothetical. In order for they could theoretically, you could just keep making elements, and you could kind of guess at some of the properties. One issue, though, is to put it on the periodic table of elements, you would have to actually find it and prove that it exists. So this is the realm of hypothetical elements. It doesn't exist yet. I'm trying to find it, though. But I can save that for the future. Is there anything else we can find from this? I'm not sure to even learn much, but let's try to go back up here. So they first found it. It was found by Albert Ghiorso. Okay. And his co-workers at Berkeley. They were working with these different national laboratories. It was the fallout from Ivy Mike, which is a nuclear test. Ooh, in the Enwatok Atoll. Whenever you see those videos of nuclear bombs being set off in the ocean, this is what they're talking about. Similar to this, it's how you would test all these different nuclear weapons. You have to test them somewhere. And unless you want to keep doing it in the desert, you can do it here in the ocean. I don't know the effect it has. It's probably not good, but they tested it in the ocean. Oh, this is the first successful test of a hydrogen bomb. Okay. Which means they would have used plutonium, not uranium. That's a bit of a difference. Okay, and at this time they thought that absorbing more neutrons wasn't realistically possible, except that it did because plutonium has to absorb the extra neutrons in order to be made from uranium. uranium would absorb it. Okay, uranium absorbs it, and then it becomes plutonium. Let's see, papers. They analyzed filter papers which had been flown through the explosion cloud on airplanes. So that's your job as a researcher. You're going to take paper and throw it into a nuclear bomb, and then you can test it for things that may or may not be on it. I don't see much else that I could even look up here. You can learn a lot about theoretically what it's like. It can help you if you are a physicist, if you're curious and pouring through some of the more theoretical aspects here. But for an actual usage in real life, I doubt you could use it. Oh, what is this? Oclo is a region near Franceville in the Haut-Ogooué part of Gabon, where they have natural nuclear fission reactors. Okay, I am now interested in this. But as it pertains to Einsteinium, I'll leave it there. If I missed anything, feel free to berate me. I'm sure somebody can. I'd like to find more interesting things in the future, so I'd probably say I'll lay off some of the more theoretical ones and stick to the ones that are known, mainly because I'm not sure what they have, but that'll be it for Einsteinium.